The tetrahedron is probably the most important shape of chemical compounds. It was discovered to be the primary structure for carbon compounds in 1874, independently by Jacobus van 't Hoff and Joseph Lebel. One of the great achievements of science to have determined the structure of chemical compounds before the advent of computer technology and electronics. So the tetrahedron can be represented in two dimensions in a number of different ways. Each of those depictions has its ups and downs, its pluses and minuses. One of the ways to examine the tetrahedron is to look at it essentially along one face. So if we're talking about the chemical compound methane, we can represent it sort of this way, where at the center we have a carbon atom. And this particular representation is useful in highlighting the threefold axis. So we notice that if we represent our methane molecule this way, that if we rotate the molecule by 120 degrees, the hydrogen atoms will all line up. Along the axis, we have a carbon atom, and behind that there's another hydrogen. But since those are on the rotational axis, they're not affected. So we see that we can find the C3 symmetry operation relatively quickly for the tetrahedron. The tetrahedron also has a number of mirror planes. None of them are going to be perpendicular to the higher rotation axis, so there isn't any horizontal mirror, but there are a number of vertical mirrors, so we could find them, for example, to be a vertical mirror here, a vertical mirror here, and a vertical mirror here in this particular depiction. Another way to depict the tetrahedron, particularly in the case of methane, is a sort of faux three-dimensional drawing where we use solid lines to show those particular atoms that are in the plane of the board. So according to this representation, the two hydrogens and the carbon atom are all in the same plane. To show something that's nearer to us, out of the plane, closer to us, we use wedges. So it's kind of a wedge there, and typically you fill that in. So that's to show us that this hydrogen is actually closer to us than the whiteboard. And then to show that the other hydrogen is actually behind the board, we use these sort of dashes. So this is a sort of way of giving a three-dimensional feel to the diagram. Now there are a number of disadvantages to this type of diagram because in the tetrahedron, this particular hydrogen and that hydrogen are one behind the other. But if we draw them that way, you wouldn't be able to see the second hydrogen. So we have to convert this type of a drawing in our mind to a representation that is consonant with the actual structure of the molecule. So in this particular representation, it's a little difficult to see, but the threefold axis essentially goes along this way. That's one of the threefold axes. It goes through the carbon and out the back of the hydrogen, and it's along this particular axis that we have a C3 rotation. And it turns out we have a number of these. We'll have a C3 axis that also comes out along the plane of the board through the hydrogen and the carbon. There's going to be a C3 there. A C3 axis going along here, again, in the plane of the board. So wherever you have a carbon-hydrogen bond, if we extend that, there will be a C3 rotation about that axis in methane. And last but not least, I won't draw it here, but we would see that going from behind the board through this carbon and through this hydrogen atom here, there will be a fourth C3 rotation. We also have C3 minus 1 if we rotate in the opposite direction. There are also a number of C2 axes, which are a little bit difficult to see, so let's erase the information about C3 and then look at C2. Now none of the C2s are going to be perpendicular to the C3 axis, so we don't have a D group. But the C2 axis tends to go, and then in this particular depiction, the C2 axis would also be in the plane of the board, and it would bisect the hydrogen-carbon-hydrogen angle and come out the other side. So here we would have a C2 axis. So the effect of this particular C2 would be to take this hydrogen to that hydrogen, this hydrogen to that one. The hydrogen that's in front of the board, that's what the wedge means, will be taken to the back, so it will be below the board. The one that's below the board, behind, will get turned to the front. So these two would be interchanged, and these two hydrogens would be interchanged, and the carbon atom itself will not move because it's on the axis. And we could just as well draw one of these C2s bisecting any hydrogen-carbon-hydrogen in the molecule. So we can go find all those. I'll show one more of those because it's not going to be in the plane of the board, but it's going to be between this hydrogen and that hydrogen. We're also going to have another C2, for example. So as far as rotational axes go, it appears that C3 is the high-order rotation axis for the tetrahedron, for a molecule such as methane. But it turns out that isn't exactly true. And we actually have a fourth-order, fourfold axis. And I'll show you where that is. And it takes a certain amount of fortuitous drawing to show what this looks like. So if we look from the point of view of the carbon, we can imagine two of the hydrogen atoms coming towards us, so they're above the plane of the board now. The carbon itself is in the plane of the board. These two hydrogens are in front of us, almost like two open arms coming towards us. And then we have the two other hydrogens are going to be behind the board. So these two hydrogens are closer, these two are behind. And we actually have a rotational axis that goes through the plane of the board. Now, if we simply look for a C2, we do have one of those along here. So if we rotate by 180 degrees, it would take this hydrogen to that hydrogen. They're both in front. And it would take the hydrogen behind to the other hydrogen behind. So we do have a C2, and that's the one we had seen, had drawn out before. But we also have a fourfold axis, and this is the one that's often very difficult to see. And it's an example, in fact, the first really important example of a improper rotation. So let me erase this for a second, and then we'll talk about how to visualize what's going on with the S4. So we have an improper rotation, which I'm going to tell you right now is an S4, and we'll show you how we get that. So S4 we can think of as a two-step process. The first step is a C4 rotation, followed by a reflection horizontal to that. So what's going to help us is, since our S4 axis is through the plane of the board along the dowel, then we know that the mirror plane that we're going to refer to later is going to be the plane of the board. Now notice that the molecule itself does not have a mirror plane there. So sigma H itself is not a symmetry operation of the group. But it's going to turn out that if we combine these together into S4, the S4 itself is going to be a symmetry operation of the group. Okay. So let's see how we show this, at least in two dimensions. Well, if I do a C4, what happens? Well, I'm going to rotate. This hydrogen is going to be pointing vertical. But since this hydrogen is in front of the board, when I rotate it, it's also going to be in front of the board. So one thing to keep in mind for later reference is that our initial situation that we're going to refer to, we have the two horizontal hydrogens forward, the two vertical hydrogens back. So let's keep that in mind. So now let's rotate the molecule by a C4, and since the hydrogens will be essentially in the same place, the only real thing I need to show is whether they're in front of the board or behind it. So I'll just show this. So now, once I've done a C4, this particular hydrogen and the one below it are now going to be forward. The hydrogen that used to be behind is now rotated to this position, so it's behind. So I can show that those are behind. And we notice that the molecule does look different after I've done C4. I can recognize that it's changed because the horizontal hydrogen atoms used to be forward, and now they're back. So there has been a change. So C4 itself is not a symmetry operation of the group. But now let me do the second step of my S4. And in this step, I'm going to reflect in the plane of the board. That means that anything that's in front of the board is going to go behind the board. Anything that's behind the board is going to come in front. So the effect of that is merely to turn the behind symbol into a front symbol, and to turn the front symbol into a behind symbol. So let me do it. So change all these around, so they just swap positions. That's the effect of the sigma H. And now I see the molecule looks exactly the same as it did before. So we see that this molecule actually does have the S4 symmetry operation. So the high order rotation axis for this particular molecule is S4. Now we had mentioned before that what we're really interested in is when we have a high order rotation axis of order 3 or more. And in those cases we have this phenomenon called degeneracy. In this case, with the mere fact that we already have a C3 means that as far as determining if there's going to be degeneracy in the molecule, we don't even really need to look for the S4. And we don't need to specifically look for the S4 to recognize a tetrahedron. However, there are molecules for which the high order proper rotation axis is only a C2, but it has an S4 improper rotation. In those cases, the high order rotation axis is an S4. Since the order of the rotation is greater than 3 or greater, it will have degeneracy. So we need to look both at the proper and the improper rotations before we could conclude that a molecule would not have this degeneracy property. So another way to visualize this, I try to come up with another way to kind of demonstrate the improper rotation. And I have sort of a paper model that kind of does this. In this case, we have here the hydrogens that are in front, and we can see that they are in front. And then this hydrogen and that hydrogen are behind. And then this sort of little square in the center is where the central carbon atom would be. And an advantage also of this little square is that represents the mirror plane that will be the second step of the S4 operation. So let's see what happens. So again, I recognize that the hydrogens on the side, the horizontal ones, are coming forward like arms ready to embrace me. And then the head and the feet are bent back. So the first step of S4 would be to rotate 90 degrees counterclockwise. And that would take us to this position. So that if C4 were actually a symmetry operation of the group, this would make it look the same, but it doesn't. So that's our C4 part of the symmetry operation. And I notice that it's not a symmetry operation of the group because now the horizontal hydrogens are actually behind the plane and not in front of it. But then remember there's a second step of S4, which is reflection in the plane of the central carbon atom, this little square. So the effect of that is to bring these hydrogens forward and these two hydrogens back. And if we do that, flip the positions, which would be the effect of the horizontal mirror, I see that now my molecule looks exactly the same as it did before. So we see that the tetrahedron really does have this property of having the S4 improper rotation. Okay, so for most of our cases where we're going to have substituted tetrahedrons, we tend to draw them in the three-dimensional style. So let's look at one example of a substituted tetrahedron. In this case, we're going to substitute it with chlorine. So this is chloromethane, so we replaced one of the hydrogens with a chlorine. And what we realize is we often will like to redraw the molecule or re-envision the molecule to highlight the high order rotation axis. So if we did this from the point of view of the hydrogens, one way I could redraw it would be like this, with knowing that the chlorine is actually pointing behind the carbon. in that case, and I can draw it on the side here, basically this is the axis that we're doing is the axis that would go through the chlorine, the carbon, and coming out this way. And I see that I actually have a threefold axis there. So I do have a C3. But in the process of modifying my molecule by replacing one of the hydrogens with a chlorine, I've eliminated most of the other symmetry operations. And the only other ones that remain are going to be mirror planes. So there's going to be a mirror plane along this particular line. And then there'll also be mirror planes that go through the hydrogen and carbon, and then through the hydrogen and carbon. So from this particular drawing, I would see that the mirror planes go along here, they go along here, and they go along here. So I'm going to have 3 sigma V's. So since the high order rotation axis is C3, and the only mirrors that I have in my compound are going to be vertical mirrors, this tells me that chloromethane has the point group C3V. Let's try another substitution. So now what we're going to do is we'll replace another hydrogen. So let me just draw the carbon this time. So I want to draw each of the molecules as many different ways as possible, and that is very useful for the student to do as well, because you never quite know which style of representation you're going to see in a paper or in a textbook. So here we have what's generally called methylene chloride, a very common solvent. And we want to look for the high order rotation axis. And we would notice that there is a C2 axis that goes actually in the plane of the board between the 2 hydrogens and the carbon. It comes out this way. And here would be our C2 rotation. This would take hydrogen into hydrogen, but also take the chlorine in front to the chlorine in back. So it swaps the 2 hydrogens and also swaps the 2 chlorines. So we see that C2 really is a symmetry operation of the group. There is also a mirror plane that's going to go right along here. So the mirror plane would reflect hydrogen into hydrogen, and then the actual mirror plane would have the chlorine in front and the chlorine behind would actually be in the plane. That's one of the things we don't get from the drawing here, is that this chlorine would in front would be on the mirror plane, the chlorine behind would be also on the mirror plane. Since it's on the plane, it's not affected by it, so that mirror would be a symmetry operation of the group. The second mirror plane is also, this is where 3-dimensional models really come in handy, would be in the plane of the board. So in the plane of the board, we have hydrogen, carbon, and hydrogen. Since they're in the plane, they get reflected into themselves. We have a chlorine in front and a chlorine behind that are reflected into each other. So that tells us that we have a C2 high order rotation axis. We have the identity, and we have 2 mirror planes, 2 vertical mirrors. So that means that methylene chloride has the point group C2V. Now if we just continue this idea of substitutions, figure, oh, let's add a 3rd chlorine and see what we get. So if we add a 3rd chlorine, and I'll draw this even slightly different again, we put one of the hydrogens here, and then we have chlorine. So the chlorine, carbon, and hydrogen are all in the same plane. We have a chlorine that kind of sticks out in front, and then we have a chlorine behind the plane, and then we have a compound that's most commonly called chloroform. So we have 3 different carbons. But we would notice that if we look from the bottom of this molecule, we could also draw it in such a way that we look up so that the hydrogen is actually behind the carbon. So if I look at it this way, I notice the 3-fold symmetry of the 3 chlorine atoms. And I would notice that if I rotate the chloroform molecule along that axis by 120 degrees, I actually have a C3 rotation. Also along the carbon-chlorine bonds, here's one, here's a second one, and here's a third one, we would find vertical mirrors. So just like chloromethane, chloroform has a point group symmetry of C3V. And if I just go whole hog and decide to replace the last hydrogen with a chlorine, now I have 4 chlorines on there. I have the compound known as carbon tetrachloride, a compound that used to be widely used for dry cleaning, but is not used so much anymore because it's widely believed to be a carcinogen. And notice that this is an identical molecule from the point of view of symmetry to methane itself, because attached tetrahedrali to the central carbon atom, I have 4 identical atomic substituents. So from the point of view of point groups, this is identical to methane. So we notice that it has the tetrahedral shape, so this belongs to the point group TD, the point group of the tetrahedron, just as methane did. We notice that it has the tetrahedral shape, so this belongs to the point group TD, the point group of the tetrahedron, just as methane did. It is quite possible to substitute the hydrogens of methane with more than one different type of atom. So let's look at an example of that. So in this particular case, let's look at where we have 1 fluorine substituent and 2 chlorines. So here we have a dichlorofluoromethane. And we want to find out the point group symmetry of this particular molecule. And if we look at it from the point of view of C2 axes, one of the axes that we had noticed before was the one along the board between going through the central carbon atom and formally involving a hydrogen and a hydrogen here. Well, we notice if we try to rotate along this axis, it would take fluorine into hydrogen. Since those are different, that would not work. We notice that the chlorine would go into chlorine, so that works, but since we have part of it that doesn't work, we do not have a C2 axis for this particular molecule. And no matter where we would try to find either a 2- or 3-fold axis, we wouldn't find any. And it turns out that the only point symmetry element in this molecule, other than the identity, is going to be the fact that in the plane of the board, hydrogen, carbon, and fluorine are already in the plane. We have a chlorine atom in front and a chlorine atom behind the plane, right in front of each other. So a mirror plane in the plane of the board would reflect this chlorine into that chlorine, even though this drawing doesn't make that obvious. So this particular molecule has the identity plus a mirror, so that tells us that this belongs to the point group CS. Now, one way when you have a model to recognize this point group in particular is if you have a molecule that can be made to look somewhat like an animal. So we think of the 2 chlorines as being the legs, the fluorine being the tail, and the hydrogen being having a head. So it has that bilateral symmetry that most of the higher animals have. It's like a human, the left side of a human looks like the right side. That gives us a hint that we have this mirror symmetry. If there are no other symmetry elements, then we would recognize that it belongs to the point group CS. Now let's take this particular molecule itself and make one more small change and see if that's going to change anything. Let's substitute the hydrogen for another fluorine atom. Let me just kind of color code this a little bit. So we have fluorine here and a fluorine there. So we'd like to see what symmetry elements are present in this molecule. If I look along this particular axis, if I do a C2 along here, it's going to take fluorine into fluorine. It's going to take the chlorine in front, the chlorine in back. So it swaps 2 fluorines, it swaps 2 chlorines. So therefore, there actually is a C2 symmetry element along this particular line. And this is in the plane of the board. So we have a C2. Also along this particular plane, there's going to be a vertical mirror. We know it's a vertical mirror because it includes the entire axis. So there's a mirror plane there. And there's also, again, the mirror plane of the board, which isn't obvious for the chlorines, but there was 1 chlorine in front and 1 chlorine exactly behind that are mirrored into each other. So this tells us that for this Dichlorodifluoromethane, it belongs to the point group C2V. Last but not least, let's take a look at one more substitution pattern and see if we can classify it. So we start off with carbon. Let me have a hydrogen here. Fluorine in front. Chlorine in back. And then an iodine over here. So we have Chlorofluoroiodomethane. And we want to see what symmetry elements this particular molecule has. And we recognize that hydrogen, carbon, and iodine are all in the same plane. We have a fluorine in front of the board, and then the chlorine is directly behind it. So we want to see what symmetry elements we have. Well, we had tried to look for C2s along this particular axis, but that would take iodine into hydrogen. Those are different. That's not going to work. No matter how I do this, it's not going to work. And in fact, now I have a problem even with the mirror plane and the plane of the board, because that would reflect the fluorine in front into the chlorine behind, and those are different elements. And we notice here something interesting, that attached to the carbon, we have 4 different groups. So in organic chemistry, this is the rule that is often used to identify chirality. So we have handedness, we have optical activity at a particular center when we have 4 different groups attached to the same carbon atom. So here we notice, from the point of view of symmetry, that the only symmetry operation we have for the entire molecule is the identity. You only have the. So that means this belongs to the sort of trivial group C1. It has no symmetry operations at all. Now, if we have a molecule like this, it will possess the phenomenon of optical activity. A molecule can have symmetry operations and still be optically active. The key rule is that for it to be optically active, it can have only proper rotations. And so that means it can't have any improper rotations. And 2 of those are kind of important, because S1 is merely a mirror, S2 is inversion. So any molecule that it possesses a mirror plane or inversion, in addition to improper rotations, cannot possibly be optically active. So using group theory and symmetry, we can develop an even more precise way of interpreting which molecules will be chiral and which ones will not.